Welcome to this lecture on modeling analysis and estimation of three-phase unbalanced power network. So, we have been talking about the modeling of a network involving a transformer. So, we have considered one simple 4-bus system in which there are two lines between bus 1 and 2 and another one between bus 3 and 4, and between bus 2 and 3 there is a transformer. Please note, we are doing everything in per unit system. So, we are doing everything in per unit system. So, our analysis is this per unit analysis. So, per unit analysis. So, it is understood that we are doing all calculations, everything in per unit system. And we said that bus, that is basically the line between bus 1 and 2, that can be modeled by an equivalent 3-phase pi model having an impedance y1 to AC ABC, that is the essentially the admittance we have written, and then two shunt charging susceptance matrices y1 to shunt ABC at both the sides of the line. Similarly, the line between bus 3 and 4 is also modeled, and the transformer between bus 2 and 3 is modeled by a 6 cross 6 matrix, admittance matrix, and we have already seen how to derive those admittance matrices for different types of connections as well as the different vector groups. And that 6 cross 6 admittance matrix can be partitioned into 4 3 cross 3 matrix y1, y2, y3, y4. And the relation between the currents and the voltages at two sides of the transformers are also shown. So, with this, let us start developing the equations. So, let us say that the injected current at this bus is I1 ABC. These are all injected current. Injected current at bus 2 is I2 ABC. Injected current at bus 3 is I3 ABC, and injected current at bus 4 is I4 ABC. So, with this we can simply start writing down the equation. So, then I1 ABC would be Y12 shunt ABC into V1 ABC plus Y12 series ABC into V1 ABC minus V2 ABC. Essentially, this injected current would be equal to this current plus this current. This current is given by Y12 shunt ABC into V1 ABC. Please note that this voltage is V1 ABC. This voltage is V2 ABC. This voltage is V3 ABC. This is V3 ABC. And this voltage is V4 ABC. Right. So, this is the current at bus 1. At bus 2, the injected current would be equal to this current plus this current plus this current. So, I2 ABC would be essentially Y12 shunt ABC into V2 ABC. Y12 shunt ABC into V2 ABC is nothing but this current. Sorry, it will not be this current. No, I am wrong. It will be this current. And then the next this current would be Y12 series ABC to V2 ABC minus ABC plus I2 transformer ABC. And I2 transformer ABC is nothing but, so it turns out to be Y12 shunt ABC V2 ABC plus Y12 series BC into V2 ABC minus V1 ABC plus I2T ABC is nothing but Y1 V2 ABC plus Y2 V3 ABC. So Y1 V2 ABC, so Y1 V2 ABC plus Y2 V3. So this I can write down Y12 shunt ABC plus Y12 series ABC to V1 ABC minus Y12 series ABC to V2 ABC. So this I can say this is equation 1. So therefore I2 is equal to, so minus Y12 series ABC V1 ABC plus Y12 shunt ABC plus Y12 series ABC, this plus this plus this plus Y1 into V2 ABC plus Y3 V3 ABC. So this is the equation for bus 2. For bus 3, this injected current would be equal to this current plus this current plus this current. So it would be Y34 shunt ABC into A3 ABC को তারপর Y34 series ABC into V3 ABC minus V4 ABC, that is this current plus I3T ABC plus I3T ABC so that turns out to be Y34 shunt ABC to V3 ABC plus Y34 series plus I3T ABC would be from this equation Y3 V2 ABC plus Y4 V3 ABC. Please note all of them are complex. So therefore Y3 V2 ABC plus Y3 4 shunt ABC plus Y3 for series ABC plus Y4 to V3 ABC minus Y3 4 AC ABC before T. So this is equation 3 and equation 4. So that current, so this injected current is nothing but this current plus this current. So Y34 shunt plus Y34 series. So that turns out to be minus Y34 AC ABC V3 ABC plus Y34 shunt ABC plus Y34 AC ABC into V4 ABC. So this is 4. So we have got 4 equations 1, 2, 3, 4. So from 1, 2, 3, 4, so from equations 1 to 4, I can write down that I1 ABC, I2 ABC, I3 ABC, I4 ABC. That would be some matrix which we will do now. And first let us do the partition. Okay, so these partitions have been made. So now I1 ABC would be, so now let us write down the elements one by one. So first is y1 to shunt, y1 to series. So it is minus y1 to ABC. This is a null matrix. This is a null matrix. Please note that this is a 3 cross 3 matrix. This is also a 3 cross 3 null matrix. Okay. All zeros are 3 cross 3. So minus y1 to AC ABC. So this is minus 1 to AC ABC. And this one. Y1 to shunt, Y1 to series, Y1. So this is Y1 to shunt plus Y1 plus Y1 to series ABC. And then this is Y2. Sorry, one thing. This is Y2. So this is Y2. Y2, and this is 0, 0. I3, Y3, V2 ABC, Y3, V2 ABC, and then Y3 for shunt, Y3 for series, so Y3 for shunt plus Y4 plus Y3 for series, and then minus Y3 for series, minus Y3 for series, and this is 0. And lastly, minus Y3 for AC V3, so it is minus and this is Y3 for shunt so this is the Y matrix, or rather this is the Y bus matrix. So again here it is 12 cross 1 vector, again it is 12 cross 1, that means it is 3n cross 1, n is 4, 3n cross 1, and this is 12 cross 12, essentially 3n cross 3n. N is 4. Also in this network n is 4. Of course n is 4 in this network. Number of bus, n is the number of buses in the system. So this is it. So again we can see that these elements are null matrix whenever there is no direct connection between any two bus. For example, here between bus 1 and 3 and between bus 1 and 4 there is no direct connection, so these are 0. But here for y1, y2, y3, y4 between bus 2 and 3 it is not the negative of the admittance matrix. So here it appears that this rule whatever we have formed earlier, that is not exactly matching, because you see although bus 2 and 3 are directly connected between with a transformer, but this off diagonal element is not actually the negative of the admittance connected between them. It is rather the admittance between bus 2 and 3, or rather the admittance connecting bus 2 current with bus 3 voltage. So it is not negative. That is the first point. Second point is that this matrix we have developed by writing down all the equations for all the buses. But now imagine a case that where there are 100 buses. So then therefore if we have to develop this matrix, it is not possible to write down all these 100 equations and then to write down the Y bus matrix. So for computer analysis we need some kind of automatic system, so that just by taking the data we can simply form the Y bus matrix by following a simple algorithm. Otherwise it is not possible. After all, whenever there is no transformer involved in the network, so that algorithm is absolutely fine. That is, we say that basically my block diagonal matrices are nothing but the sum total of the 3 cross 3 admittance matrices directly connected to that bus, and the block of diagonal matrices are nothing but the negative of the admittance connected between any two bus if these two buses are directly connected, and if any two buses are not directly connected, so then that particular off diagonal block 3 cross 3 matrix would be a 3 cross 3 null matrix. So these rules are absolutely programmable by using very simple computer code. So then therefore for any bus having hundreds, so for any system having hundreds of buses and let's say thousands of lines, it is possible to develop a simple computer algorithm to find out the Y bus matrix for a system if there is no transformer. But if there is one single transformer, then this rule doesn't appear to be followed, because here in this case as we can see between bus 2 and 3 it is actually not the negative of the admittances. And also here another point is that here we have taken this bus number serially, but not necessarily these bus numbers may be serially. Let's say this bus number may be 2, this bus number let's say maybe 1, and etc 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 etc. So then therefore again we have to write down these equations. So by writing down the equations and then to form the Weber's matrix, that is not a really very feasible process. So we have to develop some feasible process. So to develop that feasible process, what we will do is we do the following. What we do, we create one network in which we omit all the transformers. So for the given system, so my network becomes this. So this is bus 1, bus 2, bus 3, bus 4, and between bus 1 and 2 again I have y1 2 series ABC, and again I have y1 2 shunt ABC. Here also I have y1 2 shunt ABC. Between bus 3 and 4 we have y3 4 AC ABC, and this is y3 4 shunt AC, and this y3 4 shunt. So this is the network, and between bus 2 and 3 there was a transformer. You see, I will simply omitted that. So now I have gotten another network in which we have essentially retained everything of the original network, but we have simply removed the transformer connections. Now, because this network comprising of all these 4 buses does not involve any transformer, so then therefore this network will follow these earlier rules. So here if I say that my injected currents are I1 ABC, injected currents are I2 ABC, injected currents are I3 ABC, and injected currents are I4 ABC. And then by following and then by writing down the equations or by following the rules, I can simply write down this Y matrix I1 Y ABC, I2 ABC, I3 ABC, I4 ABC. This would be V1 ABC, V2 ABC, V3 ABC, V4 ABC, and first entry would be Y1 to shunt ABC plus Y1 to series ABC. Then between bus 1 and 2 would be minus Y1 to series ABC, because there is no connection between bus 1 and 3, and in fact I1 ABC would be only due to these two currents. So then therefore these entries would be all 0 and then 0. For I2 again there is no contribution from bus 3 and bus 4. So from I2 it would be essentially minus Y1 to series ABC, and then this one would be Y1 to shunt ABC plus Y1 to series ABC. Let us partition it. So let us partition it. So this is 0, this is 0, these are all 3 3. And of course for I2 also there would be no contribution from bus 3 and bus 4, because I2 is, because bus 2 is not directly connected to bus 3 and bus 4, so these also would be 0 and 0. For bus 3, again for bus 2 also, again we know that this current would be this plus this, so obviously for bus 3 the current would be this current plus this current, so obviously it would be, so, and it has got no connection from bus 1 and 2, so it would be 0 and 0. And for bus 3 it would be y34 shunt ABC plus y34 series ABC, and it is minus y34 series ABC. For bus 4 also it would be 0 and 0, because bus 4 is not connected between bus 1 and 2, and it would be minus y34 series ABC, and it would be y34 shunt ABC plus y34 series. So essentially this network is basically a disjoint network, and we have just written down the Y bus matrix for this disjoint network without any presence of transformer. Now let us compare this Y bus matrix, this Y matrix, let us say call that this is Y disjoint, with the original matrix. So we can see that if I just compare this in this disjoint matrix, now between bus 2 and 3 there are these matrices y1, y2, y3 and y4, right. So these are the 4 matrices for the transformer. So this is 2, this is 2, this is 2, this is 3, right. So now if we look at this original matrix, which is the true matrix, correct matrix, the entries 2 to entry will of this disjoint matrix only differs from the 2 to entry of the original matrix by the presence of y1. So if I just add y1, I get the original. Here it is y2, it is 0, so it is just y2. So essentially the original disjoint matrix, so here if I just do y2, so then I get this one. Here it would be just y3, and here it would be just y4. To get the original Y matrix from the disjoint matrix, what we have to do after we form the disjoint matrix, disjoint Y matrix, we simply locate the buses for which these 4 matrices y1, y2, y3, y4 are present, and then simply we add these entries y1 to bus 2 2 element, y2 at the entry bus 2 3, y3 we add at the element 3 2, and y4 we add at the element 3 3, simply. So you see y1 has been added in the element 2 2, y2 has been added in the element 2 3, y3 has been added in the element 3 2, and y4 is added in the element 3 3. So after we form the disjoint matrix, we simply add the elements by looking at the buses, or just rather by looking at the two terminal buses of the transformer. So that means if a transformer is connected, let's say between bus I and let's say bus, if a transformer is connected, say between bus K and L, K and L, this is K, this is L, right? So that means what we will do, first we will form the disjoint matrix, and then in that disjoint matrix we will add this matrix Y1 in the element Kk, we will add the element Y2 in the element Kl of this disjoint matrix, we will then add this matrix Y3 in the element Lk, these are all complex matrix, we will add this element, or rather we will add this matrix Y3 in the element Lk of the disjoint matrix, and we will add this matrix Y4 in the element Ll of this disjoint matrix. This is a very simple system, or rather this is a very simple algorithm. So first we form the disjoint matrix, and then in those disjoint matrices, by looking at the terminal buses, we just add the matrices Y1, Y2, Y3 and Y4 at the corresponding elements. So if the matrix, so if the transformer is connected at, let's say, between bus K and L, so then therefore my four matrices Y1, Y2, Y3, Y4 would be KL, KL, and then we add the element, then we add Y1 to the element Kk, Y2 to the element Kl, Y3 to the element Lk, and Y4 to the element Ll. So this is a very simple algorithm. So by this algorithm, we can find out the Y bus matrix for any network, any large network involving any number of transformers. So if there are, let's say, more than one transformer, what we will do, we will first remove all those transformers. So then therefore we will get a network which would be possibly disjoint. Maybe yes, maybe not. So for just example, just let's say that I do have a system like this, that bus 1, 2, then 3, let's say 4, and then this, and then this, and then this. So this is bus 1, this is bus 3, this is bus 4, this is bus 2, let's say this is bus 5, this is bus 6, this is bus 7, say. So between bus 1 and 3, so there is a transformer, and then there is also a line, and let's say that there is a line, and let's say there is another line from here, and let's say there is another line from here, and let's say that there is a transformer from here, and let's say there is another line from here. So this is the system. Okay. So then after that, what we will do, we will simply make a network like this: 1, 3, 4, 2. So this is 1, 3, 4, 2, 7, 6, 5, and then we will simply form the network just by removing all the transformers. So basically this is gone. So this is there because this is a line. This is also there because this is a line, but this is not there because there is no line, and this is there, right? And let's say this is there. So I have simply removed this transformer as well as this transformer. Okay. So what we will do now, my transformers are essentially between two buses, Y1, Y2, Y3, Y4. So one is 3, 4, 3, 4. and another is between 7 and 6. So y1, y2, y3, y4. Say these are all dash, another matrix, and this is 7 6 7 6 7 6 7 6. So what we will do, we will first form the y bus matrix of this particular of course there is another connection here, this connection is also there. So we will first form this disjoint matrix, and let's assume that there is also another connection between here to here. So from 3 to 6, so then obviously there is also a connection from 3 to 6. So you see, so now it is not a disjoint network. What we have done, we have simply removed the transformer. But because this network does not have any transformer, so then therefore we can form the y bus matrix following the simple rule. That is, all the block diagonal elements would be sum total of all the admittances. If there is no direct connection, there will be null 3 cross 3 matrix, and if there is direct connection, then that corresponding off diagonal block element would be negative of the 3 cross 3 admittance matrix. So with this we will be able to follow the y bus matrix by simple computer algorithm. Once we have done that, then we note that this y1 matrix would be added corresponding to 3 cross 3 3 element, right, 3 and 3 element. Y2 would be corresponding to element 3 4 of this y bus matrix of this particular disjoint network. Y3 would be added at the element 4 3, y4 would be added at the element 4 4. After that we will add y1 dash at the element 7 7, y2 dash at the element 7 6, y3 dash at the element 6 7, y4 dash at the element 6 6. Once we add these 4 plus 4 8 transformers in this disjoint y bus matrix, we get the final y bus matrix of the system, right? But still it would be a 3n cross 3n matrix, but now this matrix will have the influence of both the lines as well as the transformers. So by this we would be able to form the y bus matrix of any unbalanced power network having any type of transformer connections between any two buses and having any number of lines by a very simple computer algorithm, right? So now we have got this matrix, or rather this relation I is equal to IV. So this I is 3 cross 3 and cross 1, this is nothing but the vector of the bus injection currents. V is also 3n cross 1, this is nothing but the vector of the bus voltages, and Y is 3n cross 3n, this is the Y bus matrix, which includes effect of all the lines and the transformers. So in the next class we will start with this equation and then actually proceed. Thank you.